Yeah, great to be back. I'll tell you about an application of a language model to solving math and physics questions. But I think because probably most of you don't work on AI day to day, I'll start with a fairly detailed introduction for the techniques we're using, and feel free to stop me at any time. I feel like this part is probably as useful as the rest of the talk, where I actually talk about how to apply these models. Okay, so let me start by describing the main architecture that we use these days for solving tasks that have to do with language or generally dealing with any kind of sequence in machine learning. So I'm going to present the setup, and then we'll work through the setup in a fairly detailed manner to give you a sense of how these things are built, how we actually train them, what sort of data do we need to collect, what does the whole procedure look like. And I'll assume a basic familiarity with neural networks and deep networks, so something at the level of fully connected networks or feed-forward networks and how we train them with gradient descent, and I'll kind of try to build on that. So when we're dealing with language, we typically start by defining a vocabulary of tokens. So I'm going to use this word a lot. By tokens, I mean some roughly semantically meaningful unit, could be a word or a digit in a number or a symbol like a comma or period or anything like that. We decide beforehand on a vocabulary of these tokens. In practice, we usually learn this vocabulary, but this is not going to matter for this talk. And then we have our model is going to accept a sequence of tokens as input. And what we're going to ask the model to do is output a probability distribution for what it thinks the next token is going to be. So this is a probability distribution over our vocabulary. And formally, what we're asking it to do is to give us the conditional probability of the next token xt conditioned on all the previous tokens that came before it. This is the function that the model calculates. And to achieve this, the architecture that we're going to use, which is called the transformer architecture, it's an ordinary deep network in the sense that we have a series of layers that get composed to compute this function. It's going to have basically two kinds of layers. One kind is going to be the attention layer, which is really kind of the special sauce of this transformer architecture. This is the thing that calculates multi-token interactions, and I'll describe that in great detail. And the other kind is the feed-forward or fully connected layer, which takes every token and does some calculation on it, just like an ordinary fully connected network. And you can see on the right kind of a caricature of what this network looks like. You can see that there's an attention layer or self-attention. There's the feed-forward layer in yellow. And then there are a few other components, layer normalization, and you see these skip connections that go from the right. These are more technical details that help us train the network without it diverging, that I will not go through in this talk. I'm going to focus on these two kinds of layers, the attention and feed-forward. Everything else is kind of less important.
Each black line represents many tokens.
Each of
the vertical black arrows represent the many tokens, like tokens.
All the tokens and every token represented by a person. Here it is in a bit more detail. Here's the whole like end-to-end setup of this network in a bit more detail. So let's say that we want to give the model the input, the quick brown fox jumps over the lazy dog. That's our sequence of tokens that we want to present with to the model. And we want to ask the model to say, what is the next token going to be? So it starts on the left. We take each of these. Let's assume that each of these words here corresponds to a token in our vocabulary. So we have this vector of tokens. Each one gets some number from our vocabulary. And we end up with some large T tokens. So that's the total number of tokens we have. The first step is we take these tokens and we embed them into our model space or embedding space. So we end up with this matrix that is T by D. D is going to be the basic vector dimension by which the model represents every token we're going to have internally and then does its processing on. And so the embedded tokens live in this T by D matrix. And this matrix undergoes the transformer function. Every layer of the transformer does some kind of processing on this matrix, but keeps the shape the same. And so after we acted with the transformer function, we get another T by D matrix, which is the transformer's output. And then what we do is something called de-embedding and normalization. Basically, we take this matrix and we usually linearly transform it into a matrix of size T times size of our vocabulary. So now for every token, we have vocabulary size vector. We interpret this as unnormalized probabilities, and then we normalize them like this using a Boltzmann distribution. So imagine that after some linear transformation, we end up with this Z vector for every token, and then we transform it into probabilities like with a Boltzmann distribution. So what we end up with is this matrix T times size of the vocabulary, where for every token, we simply have a probability distribution over our whole vocabulary, and that's the model's prediction for what that token should be. Now, notice that we get this for every token. All the ones we know, let's say, except for the first one maybe is less interesting, but like all the ones we know plus the next one. So really the model is outputting not just a single probability distribution, it outputs T probability distributions. And so it's giving us a prediction for every token based on everything that came before it, which is very nice because that means we can sort of take all these predictions, look at what the token there actually was, calculate the error, and sort of train on all of these things in parallel. Okay, so that's the forward step of the model. Now we'll focus on this transformer function and what it actually does. What are these layers that do this calculation? So first we have the feed forward layer. This one is very simple. Again, let's say that the thing that goes in, this is this black arrow. This is our input into the layer. It's a T by D matrix. And the feed forward calculation, it's a simple 2-layer feed forward network acting on every token individually. So again, the first dimension of X is the sequence index or the token. And the second dimension is this internal representation of the token. We're going to have for each of these layers 2 weight matrices, W1 and W2, let's call them. So we have a linear transformation, then we have some nonlinearity, something like ReLU, and then we have another linear transformation. So that's it for the feed forward. It acts separately on every token. The next part is a bit more involved. This is the self-attention layer. And this is the thing that calculates that gives us the multi-token interactions. So first I'll describe the general idea of this layer, and then I'll give all the formulas so you can see how it actually works. So the idea of self-attention is for every token, we're going to calculate a mask or a set of weights over all the previous tokens. That these weights are supposed to tell us which of these previous tokens are most important for trying to predict what's going to go in this next token. So maybe there is a token that's very far back that's for some reason very important for determining what this next token should be. Or maybe it's just the last token, or maybe they're all equally important. This mask is there. And so for every token here, and sorry, this is flipped. So now the network goes from top to bottom. Top is input and bottom is the output. So for somewhere in the middle, we have some token. The token calculates the mask over all the stuff that came before it. And then using this mask, we calculate a weighted average over everything that came before it. And we use this to get the new value at that token position. So that's at a very high level. Here is how this actually works. So again, now we're looking back. Yes.
So what does it mean that this is the output? Is the output the probability, or what are these Z's?
Yeah, so these Z's, let's look here. So the Z's are these guys, the transformer output. They're not probabilities yet. They're just some vector in the same dimensional space. Then we take this, we want to convert these into probabilities. So we do a linear transformation that just changes the shape of it changes every vector that's d-dimensional into a vector that's sigma dimensional. So now we have something that we could maybe interpret as unnormalized probabilities, and then we just normalize them. And we rely on the training procedure to turn these into sensible probabilities, but there's nothing in the architecture that says that these should be like probabilities.
D is a free choice.
D is a free choice. Let's say D is, it changes with the size of the network, but let's imagine that it's 1,000. That's a typical, pretty typical number. And the size of sigma would be, let's say, 50,000. Let's say that's a typical size for the vocabulary. Okay, so now we're looking at this self-attention layer to see what it looks like. We have X, again, as usual, when we're going through the model, X, the input is this T by D matrix. Then we're going to have some weight matrices, which I'm simplifying somewhat, but for this purpose, they're just going to be square D by D matrices. And then we start calculating a few things, building up to this attention mask or these set of weights that are going to tell us for every token, which are the most important previous tokens to attend to. So there are a few steps here. First, we compute these three matrices called the queries, the keys, and the values. These are obtained simply by taking our input X and applying three different weight matrices to it, WQ, WK, WV. These are all D by D matrices, and these are learned. These are the model parameters. These are part of the model parameters that are going to be learned, or the weights. Then we take these queries and keys and we calculate this QK transpose. This is a T by T matrix. Okay, so we have a square T by T matrix. Again, T is the number of tokens. So you can see that already this is something that's going to be used as like a bunch of weights. Weights or attention weights that can be used to tell us how important every token is. Let's skip this M for a second. So let's say we have this QK transpose T by T matrix. And then what we do is we normalize this row by row. We treat every row as a set of unnormalized probabilities or unnormalized weights. And then we take and normalize this row by row, again, just by doing this Boltzmann or softmax function to turn these into something that sums up to 1. Right? Now this gives us the thing we call the attention mask A. So it's a T by T matrix where every row sums up to 1. And then we take this matrix and we act on the values, which again are just some vectors that we derived from our inputs X. So that basically we have every row is some weights. We have our values corresponding to some values of the tokens at these positions, and we act with the weights on these. So for every token, we get a weighted sum of everything that all the other tokens. And the only wrinkle here is this M. This M is introduced, so this means element by element multiplication between this matrix and the M matrix, which is also T by T. What this M does is it erases all the values that are to the right of the token that we're looking at, so that it sets them to 0, so that every token can only attend to the things that came before. So that just means that for every token, we look at everything that's to the right of it and we assign it 0 weight. So this matrix is simply a lower triangular matrix that has 1s under the diagonal and 0s on the diagonal and above. So it just enforces causality here, meaning that we look at a token, the token can only depend on everything that came before it, or the new value for the token can only depend on the things that came before it. So just to go through this quickly, there is some procedure here for calculating for every token a set of weights that sum up to 1, that look at all the tokens that came before this token. This ends up being a big T by T matrix A. And then we take this and we calculate the weighted sum for every token using this mask on this set of values. And this becomes a new value of all the tokens. So we get a new T by D matrix where we've updated everything based on this calculation that involves all the different tokens. So this isn't like a two-body interaction. This is actually a multi-body interaction because we're normalizing over all these previous tokens. So it's a fairly complicated interaction between the various tokens. This is the whole up to these technical details of layer normalization and so on. This is the full transformer network. So any questions until here?
Did you tell us how to get WQ, WK, and WV?
I will say, yeah, next slide, you'll see how to get those. Yeah,
Thank you.
these are the learned parameters of the network, just like, so the set of learned parameters are these W, Q, K, and V, plus these W1, W2 for the feed-forward network. This is the full set of weights of the network. Okay, so that's the next question, is how do we actually train these models? How do we find the correct weights? So it starts by collecting data, because we're doing supervised learning here, so we need a data set to train on. And so this data set, it should be a data set of some documents. If we're doing natural language, this could be documents from Wikipedia or news articles or books or whatever it is. If we're doing this on DNA, then these should be DNA sequences. Some set of documents representing long sequences. And then we take these documents, we split them up into token sequences that fit within the model. And then given a sequence of tokens, imagine this could be a Wikipedia page, or the token is corresponding to a Wikipedia page. We're going to try to train the model to say, look at a prefix, look at a set of tokens in the beginning of the article, try to predict the next one. And we do that for all the tokens in the document. And so if you're used to something like a feed-forward network where we have inputs and then targets or labels or outputs, here, every token participates both as an input for many prefixes and as the target for the next token predictions. And this is called autoregressive training. And so we're going, again, to try to train the model to say for every token, try to predict, so for every sequence of tokens, x1 through xt minus 1, let's say the first sentence in the Wikipedia article, try to predict what is the next token. And this is the loss function that we use in practice. It's standard cross-entropy loss, where we take the model predictions, P, which depend on the model weights, for every subsequence, and we calculate the model's probability distribution for the next sequence, and we evaluate that probability at the actual token xt. So we know what token actually came next in the document, and that's going to be our target. That's the probability that we ask the model to actually evaluate. And then we compute the cross entropy or the empirical cross entropy for this, average over all the tokens in the document, and that's going to be our loss, right? So we end up with a function that depends on all these weights, all the W's in the feed-forward network and the W, Q, K, and V in the attention layer. We have a function that's also happens to be differentiable with respect to these weights, and now we do gradient descent on this function. So that's how we train these models. And this thing scales up very nicely so that we can actually train these models on good chunks of the whole internet. So that's how you find the W, K, Q, V, all the model parameters. And now with this model in hand, we can actually use it to generate text. And the way we do that is we give the model some context, some input, and then we compute the next token distribution, and we sample from it with temperature. So far we just use we use the Boltzmann distribution with temperature 1. When we generate text from these models, we can actually choose a different temperature. So we take these probabilities P that come out of the model, and we renormalize the probability distribution using some inverse temperature beta. So we get new probabilities, and we use those to sample from the model. And what this parameter beta, or what the new inverse temperature gives us, is it's a trade-off between how accurate versus how diverse we want the model answers to be. So if we set this temperature to 0, that means we are always only picking the most likely, or what the model thinks is the most likely continuation, which should be the best continuation. And we'll always get the same answer, but if we set the temperature to be a bit higher, we'll start sampling from the rest of the distribution. We'll get more diverse answers, but perhaps less accurate ones. So we do all of this to get the next token, and then we can add this token to our prefix and repeat. And so we generate things token by token. And so we can generate long sequences of text in this way.
You start with just one word and then generate. What do you start with?
You can start with any sequence.
Okay.
That it could be a question, or it could be like the beginning of an article, or any sequence that you want. And then you start sampling token by token to continue to complete it.
So as you add more things in, your sequence length is getting longer?
Yes.
Okay. Well, what's the typical size of this length?
So these models, they typically fit let's say 2048 tokens was pretty typical. We can now train ones with 8,000 or 16,000 token length. It's like words. It's like about 8,000, 16,000 words. That's kind of the limit right now.
Okay. Page.
Yeah, 8,000 would be like I don't know, like a 10-page paper. I'd say roughly you can fit in there. Yeah. But,
How flat is this distribution for the next token typically? I mean, obviously, if you just put in it can complete in a bazillion ways. So how flat does it, how sharply peaked is it, or how flat is it? Kind of as a function of the input length.
It completely depends on the context. So if you ask the model, if you say 2 + 2 =, it's going to be extremely sharp on 4. But if you just say then it's going to be, entropy is going to be very high. So it's going to be very uncertain about what comes next. So
Yeah, but I guess I was asking in the cases where it's like pretty sharp, how sharp is it?
Like 2 + 2 =, you're going to get something. I forget what the number is exactly, but it's very sharp. Like you'll have to turn up the temperature pretty high to get, like, even at temperature 1, I think you're almost always going to get 4. Yeah.
Okay.
Is it restricted to have just one token per time, or is it a way to get like subset of tokens, and would the answer change, or would the thing be less restricted to not work token by token? Or is it going to incorporate that in your procedure?
Yeah, that's a good question. So with these models, we're really training them to do this next token prediction. And so there are, let's say it's like this, people are working on ways of relaxing this a bit, because this is very, it's inefficient in the sense that we can't really parallelize sampling lots of token. We really have to do it one by one, which makes sampling pretty slow from these models. These are, I would say, tricks or hacks. Like the basic thing is, yes, you sample token by token, because all the model knows how to do is calculate these conditional.
Can you define a token that is just several tokens, and that's it? Yeah.
Oh, I see. Well, you can in your vocabulary, you can define whatever you want. Yes.
It's not restricted. Or that's what I was asking.
Oh, I see.
It's a trivial thing to redefine your token such that you can, like, if you want to compute a sequence of words, you can define a token as any kind of pair of words such that you can.
You can definitely do that. Yeah, you can choose your vocabulary to be whatever you want. Yes.
So question about basically loss function or probability. So stop marks of those output features, is it the conditional probability or the probability of x1, x2 so on to xn, or it's conditional xn, conditional x1 to xn minus 1?
The thing that the model actually calculates, it's this conditional. Yeah,
It's already conditional.
Yeah, it only calculates the conditional.
Also, the datas were not all independent, right? So was there a reason that you separated it to? For example, like there was, I don't remember the notation, but it was like 1W times another W.
Like this one?
No, like yeah, here, I don't know, like everything depends on WQ times WK inverse, a transpose, right?
Yes.
But not separately. So is there a reason that you train different separately?
As opposed to just multiplying them?
Yeah, just define this as one matrix and just find.
Yes, yes.
The dimensionality is smaller?
In the case I presented, it's not smaller, but there are, let's just say that it's useful. It's true that in this case, you could just like combine them, and it would change the training dynamics a bit, because gradient descent is not the same if you have one matrix or if you have a product of two matrices. The dynamics are a bit different. In this case, it probably doesn't matter, but this is the basic setup, and there are many variations on this, which actually make use of the fact that these two guys are different. So I mean, there are things like multi-query attention, and it is actually pretty useful to keep these things separate in the general setup.
So, but T usually is larger than B, right?
So square matrices. W. They're divided.
Yeah, I wouldn't say T is usually larger. Sometimes.
Is there any
I don't know.
approximation that you can make if T is much larger than D or vice versa, that is helpful, or do you just take any fixed finite value and whatever you just don't consider any theoretical approximation?
The thing that happens when you try to, so the thing that happens when you try to make T very large, if you go through and calculate the complexity of this calculation, you find that there's a piece that's linear in T, and then there's a piece that's quadratic in T because you have this T by T matrix, right? So typically, we like being in the regime where it's not just that D is very large, but like the whole network is quite large relative to T in a sense. So I mean, precisely, we typically want the linear piece in the complexity to dominate so that we can scale things up and they're still linear in T. If you try to make T very large, you hit this quadratic piece that becomes dominant, and that's kind of when it becomes inefficient.
In that case, you have to increase D.
You increase D, but you can also do that by increasing the number of layers. You can increase, yeah, those are the two main things, let's say, number of layers in D, yeah. Otherwise you have to do other tricks to make it efficient, because this quadratic piece starts dominating and the whole thing becomes very slow.
There are many blocks of this transformers, right? I don't see 12 or something.
Yeah, it could be more.
Do they share weights?
No, they don't show this.
So when you optimize the loss function, what are you optimizing for?
We optimize the W's. W's are the variables that we're doing gradient descent on. So basically, we're asking the model to predict the next token. Then we calculate the probability that the model assigns to the correct next token, which is xt. So that's this function. And then this whole function depends on these W's. So the W's are the things that we actually update in gradient descent.
Yeah. So my question is, what does the W depend on, and from from one particular P to another?
What does W do?
I mean, how are the P's distinguished from one PW to another PW? What distinguishes them?
I mean, the P is a function of the W's, right? It's a function through all these calculations that go in. So these like all these linear transformations and so on. So P is a composition of all of these calculations essentially. And so P depends on all the W's. And so when we update the W's, the P will change. This is just like in ordinary fully connected network where you compose all these functions that involve linear transformations that include the weight matrices. And then once you update the weight matrices, you've also changed the function that the model is calculating.
I see.
Shouldn't the data appear here in this loss function? Shouldn't be like the difference between the prediction and the data?
Yes, this is where the data comes in. So this is the prefix. And we're calculating PW, and then we're evaluated on the actual next token that appeared in the data. So PW is a whole distribution.
Okay. Oh, okay.
Okay. So this is like the label, and this is the input. Yeah.
Sorry, and why is this the right thing to minimize? Is just a guess, or? I understand why it's a good thing to do it, but I can think of many other functions based on the P's that.
Yes, so this has a few nice properties. It's definitely not the only function we could use. I mean, we could just use mean squared error if we wanted to. There are a few things that make this nice. One is that this approximates the cross entropy between the distribution that the model predicts and the actual distribution. It's like there is implicitly kind of I mean, the full thing would have like a Q log P, where Q is the real distribution, the ground truth distribution. And this is an approximation in the sense that the Q that shows up here, it's implicitly there because we're imagining that we sampled the real data from the ground truth distribution. So just the very fact that the samples we have are already weighted by whatever the Q is. And so that's why this is an approximation to the cross entropy. The cross entropy, it's like, it's the relevant part of the KL divergence. So it's a good measure of it's a sensible measure of the distance between the correct distribution and the distribution of our model P. So in that sense, if you think cross entropy is a sensible thing to do, this approximates the cross
Entropy is what we call relative entropy.
I think so. Yeah, I think so.
Right.
KL divergence.
KL divergence is like, this is
divergence is the relative entropy.
so this is the piece of the KL divergence that actually depends on PW. There's another piece here, which only depends on the ground truth, which we don't put in here. And from a technical perspective, this is a convex function, which also tends to be nice when you're trying to do optimization. Just the log P is convex, not the.
You mean you're keeping the Q log P piece and not the Q log Q piece?
Yeah, exactly. The Q log Q is I don't need it because it doesn't depend on W. So when I calculate the gradient, I don't need that in.
Can I ask you said it quickly, but does it work a lot worse if you just do something like summing square differences? Is it qualitatively the same, or is it really much better using relative entropy?
In my experience, I haven't tried it on language models, but I can say on vision, this works much better.
I see. And you're probably going to say it, but roughly how many weights, how many parameters are you going to be talking about in your realistic examples?
So between a few billions and hundreds of billions.
Thanks.
Asking what kind of function to put here.
Yeah.
This is not a question that must have a unique answer, right?
Yeah.
So a priori, it's not that you know that there must be a better answer out there. You just haven't found.
That's right.
This is a problematic choice.
Yes.
Okay.
Somewhat motivated by theory, but at the end of the day, a pragmatic choice. Like I can give you an example of why this is better than mean squared error. Mean squared error has an issue where, if you train a linear model with mean squared error, if you set your learning rate to be too high, for example, bigger than 2 over the curvature, then the thing diverges. Right. So it's pretty sensitive to learning rate choice. And this log is asymptotically, because of the softmax that's hiding in here, asymptotically, this thing is linear when you take the weights to be very large. So it's much less sensitive to learning rate, for example. So it actually tends to have like practically useful characteristics, but definitely, I'd be surprised if this was the optimal choice for this. Have to speed up dramatically. Okay, so this, I think, Jared gave a talk here where he probably showed some plot like this. So I'll review this very quickly. So one thing we see with these models, now jumping ahead, is we take a lot of these models, we train them on lots of textual data. And when we do this, we find that the way these models perform is somewhat predictable. So this is a plot of every line here is the training curve for a particular model, where the x-axis is compute. How many flops did we actually invest in training this model, which is proportional to the number of tokens we showed the model times the amount of compute spent when we do forward and backward pass in the model. And then y-axis is the test loss. So it's precisely taking this loss and calculating it on a bunch of unseen data. And we see that while the curves themselves have somewhat of a complicated shape, if we go to a certain amount of compute and we ask what's the best loss that we can obtain if we invest this much compute, so that could mean like a smaller model trained on more tokens and vice versa, we see that these optimal test loss follows a very nice power law that spans multiple orders of magnitude and has since been extrapolated further. And so on this very rough measure of test loss, we see that scaling things up and sort of investing more compute in them and showing the models more data leads to predictably better performance. This very coarse grained metric. We also know that scaling things up leads to a qualitatively better result. So this is an example from a different domain. This is from image generation, but still it's a transformer-based model. And here the question is, the goal of these kinds of models is to say, here's a caption, please generate for me a picture that corresponds to this caption. So here it's asking the model to produce a portrait photo of a kangaroo wearing an orange hoodie and so on and so forth. It should be a Sydney Opera House in the background, should be a sign that says welcome friends. And you can see how starting with a model with 350 million parameters and then scaling it up and training it on more data leads to qualitatively better results. It's not just on these dry metrics that we see improvement, we see actual real improvement. So it starts with something where the smallest model produces a sign with illegible text and the thing in the background is not the Sydney Opera House. And the 20 billion parameter model really nails the caption and gets all the details of it correctly, including the text on the sign. So the general lesson here is that bigger models trained on more data tend to do much better. And our question in this work was, can we apply the same to quantitative reasoning tasks? Can we apply this to a model that can actually answer math and science questions? Yeah.
How is the previous one related to your model? Because you only had a set of token, which was word, but then you are predicting your picture.
Yeah, sorry, this was a bit of a jump. So, but the way these things work is these tokens don't have to be language tokens. They could also be something that corresponds to pixels, right? Because the tokens don't have to be like words in a language. These are just abstract vectors. They could be anything. And there is a way to adapt this transformer architecture that I described to outputting not natural language, but pixels that form an actual image. So I won't go into that, but I ask you to believe me that the thing that generated these images at its core is the same architecture, or almost the same architecture that I showed before. If you want to see more, there's this particular thing is from a project called Party from Google. They have a paper on this, which builds on previous papers. I mean, the basic thing here is called vision transformer. That's like the application of transformer architectures to vision and image.
Sorry, and the scaling is on the data instead or the training?
So that's by scaling, I mean, you show it more data and you make the model bigger. So you make B bigger, you give it more layers.
Explore all the data you have in the world at this time, which is actually reasonable. Then you can still make it better or
if we run out of data, then it's hard to keep making it.
I mean, you can produce new data, but then you can use again to train, but then I guess that has problems maybe. You know, because if you produce not like perfect data, then you use it to train it and it can be some kind of feedback, which is maybe problematic.
You're talking about producing more data with humans or with
no, not with humans,
with the model?
Yeah, I mean with humans it might take time to produce it.
Yeah. So that's something that's we're just starting to explore now.
Yeah.
It seems that short term there are gains to be had by letting the model produce its own data and training on it. And if you're asking long term, are we still going to see like a trend like this? Sorry, using data that's generated by the model? Probably not.
I guess you still have, I mean, you have access to most of the internet already, right?
It's not
not really does, but you know.
Yeah, I don't think we're. Yeah, I haven't trained on the whole internet yet. That's very expensive. Like maybe in 10 years or so, this will happen. And then we'll have to deal. Yeah.
And you're gonna differentiate between data from humans from data from produced by this method.
Even now, I would differentiate between data we just scrape from the internet and data that's being produced by humans for the purpose of training these models, like they did for ChatGPT. Even there, like I would say, some distinction. Yeah.
What about the quality of the data? Because you mentioned just by increasing the quantity, these would improve. But I mean, quality is perhaps hard to quantify.
Yes.
But I mean, surely that would change the slope or whatever.
Yeah, I think I mean definitely that's true. If we show it garbage, then we will get back garbage. And I mean my mental picture, it's a bit like drilling for oil, where in the beginning you get a lot of high quality stuff. But if you actually were to use the whole internet, there's a lot of garbage in there. That's very hand wavy. I don't really know how to quantify it. I can tell you that when we train these models, it is actually useful to train other models to determine the quality of different documents and only keep the ones that have like high quality. These are useful things to do, but I don't know quantitatively how to connect that with like the exponent we're seeing here.
And not all pictures on the internet are associated with captions. So how do you, not all diagrams or pictures on the internet are associated with captions which describe them. So how do you train the model in this case?
Oh, you don't. For those image generating models, if you don't have the caption, then I think you just don't include that in the training set. But there are enough out there that have captions that.
Let's let Guy
I see.
tell us what it was.
Okay, so the question here is, yeah, can we apply the same technique to math and science questions? And the approach we took here is very similar to what I described before. We start by collecting a large data set of documents. The main criterion is going to be that they contain some kind of math in them. And then we train a large model. I'll explain what all this means, but basically train a large model on this set of documents. And then we apply some inference type techniques to improve the quality. So let's go through this, but before we go to the details, let me just show what do we get when we take a large language model and we train it on lots of math data like archive papers and things like that, and then we start asking it math questions. So this is an example from a benchmark that's called MMLU. This is a large multiple choice benchmark. And so here we have a physics question. So we have a uniform solid disk, starts from rest and rolls down an inclined plane without slipping. And then what is the fraction of the disk's total kinetic energy? That is rotational kinetic energy. And it's a multiple choice question, so we need to figure out the correct ratio. And this is the model's answer. After all the bells and whistles go in and we sample an answer from the model. And again, the answer here is produced, just like I said before, token by token. We show it the question plus a bit of stuff before, and we just start sampling from it word by word or token by token, and it produces this answer. So it says the disk has both translational and rotational kinetic energy, and then it introduces some of these symbols. V is the speed, I is the moment of inertia, and so on. It writes down the formula. This is all in LaTeX, and you're seeing the rendered form, but input and output here are all in LaTeX. So this is the translational energy. This is the rotational kinetic energy. And once it does this, it plugs in the moment of inertia for a solid disk, which I have to convince myself is correct, but ends up being correct. Simplifies a bit, and then it says, oh, so we need to calculate the ratio. So this is the ratio, plugs in the previous result, simplifies, gets 1/3, and then says the answer is B. So that's roughly the level where it's at. This is like early college, or let's say end of high school, and those are the kinds of questions that this model is able to solve fairly reliably. And yeah, as I said, this is all happening in LaTeX, and we're just rendering it to make it look pretty. Let me skip this. Yeah, it does very symbolic calculations. So yeah, here it needs to find the center of an ellipse. So it just starts simplifying, completing the square and so on until it gets to this form, and then it reads off the center of the ellipses, -4, 1. Okay, so let me describe the training details. So really the main new thing here, yeah.
Right. In the last slide, if you don't give it the text prompt and you just say whatever your equation equals question mark, can it also do the same task?
Sorry, can you say that again?
Like let's say you're not giving it a task where you say like, find the center of the ellipse whose equation is blah blah blah. But you just give it some like equation and then which you can specify purely symbolically and ask it to solve it. It'll still be able to do that.
Oh, so solve an equation?
Yeah.
Okay, can solve equations. Yeah, for sure. I mean, this one has 2 variables, but you can say solve for X.
Yeah.
And then it will solve for X. Yeah, that it does. Okay, so how was it trained? Really, the main new thing here is the data. So we know that large models trained on lots of data do well, but the large models we have trained on general data from the internet don't do well on questions like this. And so the trick here was to focus the data set a little bit on the things that we actually care about, which is math essentially. So the data set has 60 gigabytes of documents that have some mix of natural language and math in them. They come from 2 sources that are roughly equal in size. So one is archive, so it's all of the archive in LaTeX form. And then the other half is all the web pages we could find that contain some math in them. Right, so we took the web pages that Google scrapes from the web, and we filtered them for those that contain math in MathJax or MathML, if you're familiar with those plugins. And then we processed the data. So archive papers didn't need much processing, but for the HTML pages, we kind of removed all the HTML tags, that we kept the LaTeX in there.
Sure. Do you also include the wrong math? Pages? I mean, sometimes if you go to practice, change it at wrong answers and people, oh, you don't do this, you do this. No, you include everything. You have also the room for switchers.
Yes. You don't know how to at scale.
No, I mean, no, that's fine.
Papers also have mistakes sometimes.
Yeah, no, exactly.
Yeah, it all goes in there.
Guy, it's surprising that for high school level or early college level physics and math, that archive papers could be important. So what happens if you just throw out one and just keep two?
Yeah, that's a good question. I don't know the answer to that. I mean, I can say this model can do more than solving math and physics questions, but we didn't have the budget to ablate archive or non-archive. I mean, I agree with your guess. I mean, I think if we remove archive, it's probably not going to suffer too much on like solving math questions at a high school level. Probably. Yeah.
And number two includes like most math textbooks and things like that, I guess.
No textbooks. No textbooks. Because those are really just HTML. So I think most of those are not accessible in HTML form, so they would not be in there.
I see.
Okay, then this is how we train the model. So here there's something we do with deep networks, which is called fine tuning, which is to say you can train a model for a while on some data, and then you take that trained model and you keep training it on different data. And if these data sources have kind of similar distribution, that's a pretty good thing to do. You end up getting better performance than just training from scratch on your smaller data set. And so this is what we did here. We started with a pre-trained language model called POM from Google. This was trained on just general scrape data from the internet, Wikipedia, some books. This model comes at 3 sizes, from 8 billion parameters to 540 billion parameters. So we took these models and then fine-tuned them on this technical math data set that I just described. And just to give a sense of perspective, the largest model here was trained for a month on 1,000 TPU chips. It's like 1,000 GPUs per month. And these are some numbers. I think we talked about these numbers already, but you can see that these models have between tens and like hundreds of layers. A layer here is like one of the transformer blocks. We didn't talk about multi-head attention, but the model is what we call deep. You can see it's between a few thousands and 18,000. Okay, so now I'll describe, given the model, there are a few things. If you just take this model and you ask it a math question, it doesn't actually do very well. There are a few simple things that we do to kind of get the best performance out of it. One thing is few-shot prompting. So it turns out that it's useful to, instead of just asking a question, the input is going to be a few questions and answers, and then the question. And that's enough to prompt the model to kind of answer in the same form of the answers that it saw before. So for example, when we ask it simple arithmetic questions, we give it this prompt, just a few simple arithmetic questions and answers, and then we ask it back.
Is this done during training or after?
This is all. At inference time means after we're done training, we're just using them all. So we're not training on any of this. It's just part of the input.
Sorry, the prompting, is that just setting the context, or you need to really design the prompt? I mean, is there any relation between the first sentence and the final question, or it's just setting up a mathematical context?
Yeah, if you give it this prompt and then ask it a history question, it's not going to do very well. So it's useful to have the question you ask it be kind of similar to questions that show up.
Sorry, but I think actually it's kind of the same question, that if you show it that prompt and then ask it to find the center of the ellipse.
Yeah, then it will not do well. Probably.
That doesn't help.
That's right. And this is going to show why. So the next step is using chain of thought prompting. This is where we give it again like a set of questions and answers, but the answers now, they're not just the final answer to the question. The answers we show it are step-by-step solutions to the question. Okay, so this is what we actually use to solve these high school level math questions. We have a fixed 4-shot prompt, so a fixed set of 4 questions and answers that look like this. So like this is actually the first one, find the domain of this expression, and then solution, the expressions inside each square root must be non-negative, and so on and so forth. And then this is the answer. And then they all end with, I hope it is correct. This is because this prompts the model to also say, I hope it is correct. And then it makes it easy for us to isolate the answer. We just look for everything. We look for the, I hope it is correct. And then we just look for what came before it. I don't think this affects the performance. So this is really what it looks like, 4 of these. And then we ask it the actual question, let's say this one, and then ask it to complete, okay? And just showing it a few examples of step-by-step solutions causes the model to try to output a step-by-step solution, like the ones we saw before, yeah.
The data that you train the weights on, do they typically have this, you know, like show your work type setting, or like since the weights are already trained, why exactly does giving it the chain of thought prompting help it in any way? How does it know to correlate that with what it's already doing?
I don't know is the short answer. Probably a lot of the data has these patterns, some kind of pattern in there of like, I don't know, question answer or things like that. But this prompting techniques works much more generally than on math. Like just showing examples tends to make these models do better. And I don't know why that happens. It was discovered in the GPT-3 work that these models can do this kind of few-shot learning or in-context learning. And I don't think we really understand why that's the case. No. Okay, and then the last thing, which to me was the most surprising technique that helps, is majority voting. So we can take the model, we can give it the prompt, we can ask it a question, and then sample from it at some temperature. If we sample once, then it's best to sample with 0 temperature, just give us the most likely token at every step, and this gives the best performance. But the better thing to do is to use finite temperature, sample about 100 times from the model, get a bunch of these chains of thoughts plus final answers, and then take an answer with the most common final answer. So it's as if we're letting the model vote on what the final answer is, right? We're sampling multiple times, we're seeing a bunch of final answers, and then we're choosing the most frequent one. This boosts performance like almost as much as the whole fine-tuning that we did. So this is, for some reason, this helps a lot. And that's it. That's the set of techniques we had. I think, yeah, let me skip this because I'm almost out of time. Okay, here's some results on the math benchmark. So remember the question we saw earlier. This was a question from this math benchmark. So it has a variety of difficulties in it, going up to qualifying high school Olympiad questions. That's roughly the hardest questions in this particular math benchmark, about a few thousand questions, and split up by different topics, algebra, number theory, and so on. You can see the overall performance. Let's just look at this bar, which is the 540 billion parameter model. You can see that on 540B, this is the basic model without any fine tuning on math, does about 10%. And then going from here to here, that's the fine tuning we did on Minerva. This is all with this chain of thought prompting. You can see we're up to 30-something%. And then just adding this extra majority voting thing where we sample 100 times from the model and take the most frequent answer, this brings up to a bit over 50% accuracy on this benchmark, which is, it's a fairly difficult benchmark, and this is state of the art. I'm going to skip this and this. There's some mistakes. I want to show the weirdest mistake. I think that's probably good. So we have, I mean, the model obviously makes mistakes, even on the benchmark, we just get like 50% accuracy. So it makes many mistakes, some calculation mistakes, some logical reasoning mistakes, but sometimes it also has false positives. That's when it produces a whole incorrect chain of thought and then does give the correct final answer. And some of this might be due to memorization, like maybe some of these questions did appear in the training set, also, although we worked hard and we found a few examples, but very few examples of things that were in the training set. But we don't really have an explanation for this. Our estimate is that about 8% of the model answers are these false, of the correct ones are these false positives. So that happens. I wanted to show, maybe in the last 2 minutes. Yeah, let me show these two examples. So here's an example where we try to, I wanted to find a question where the model needs to recall some non-trivial fact and then use it. So this is a question like I made up. So a rock is dropped from the height of 2 meters above the surface of Mars. What will be its velocity when it hits the ground? So you see the model that we know that the acceleration due to gravity on Mars is 3.711 meters per second squared, which I have to look up, but is correct. And then it uses conservation of energy to figure out the velocity and takes the square root and calculates the square root somehow. And this is fairly accurate. So I thought, well, I came up with this question, but it must have been memorized. So I tried to put in different numbers. And when I plug in different numbers, it could no longer take the square root, but it still ended up with an answer with the square root on it that was still correct. So still these kinds of questions it can answer. Maybe yeah, that's the last example, really. All right, so yeah, the takeaway is pretty simple. If you scale up these models and show them lots of math data, they get good at math. And the other lesson is that these inference time techniques like chain of thought, prompting, and majority voting, they boost performance by a lot, which means that we also don't really understand the full capabilities of these models that we train. Yeah, thank you.
Maybe a curiosity. So when you were showing the results of the various tests in the various subjects, it seemed like it was quite different depending on the subject.
Yeah.
I think like algebra was doing very, very well. And maybe, yeah, calculus not so much. Do you have any idea why that's the case? Is that the format of the questions or the?
Some is the format, like geometry questions have a lot of figures in them. So those tend to be more problematic. Intermediate algebra is definitely harder than algebra, so it's also a difficulty thing. The other ones, yeah, I think the algebra ones tend to be easier, let's say, than like the number theory ones and the calculus ones. I think it's mostly about like average difficulty within these subjects. Yeah.
When it comes to the LaTeX that it learns in order to generate the outputs, do you somehow like pre-process the data and normalize the notation? Like how does it know? So given that you're just taking some examples from the internet and probably all kinds of different notations for the same concept are going to show up, how does it know how to tokenize that and then pick, you know, okay, I'm going to choose K for kinetic energy as opposed to some other random symbol?
We don't do anything like that.
Okay.
Show it the data as is after we remove the HTML tags. But
sure.
Other than that, it's just LaTeX. We don't normalize symbols or we don't know how to do any of that at large scale. So it's kind of the best we can do is just give it the data.
So somehow it just associates a high probability to like the most sensible symbol it could.
Yes.
Kind of interesting.
Probably because frequently when you have speed, it's usually use V to.
Yeah, so the VF and VI, but like the fact that it chose K for kinetic energy as opposed to, I don't know, T or whatever else people use like that.
Well, I'm sure that if you look at the actual distribution there, I mean, capital T is probably going to be high up there as well.
Okay.
Yeah, just based on frequency in the training data. Yeah.
And do you sample the tokens like just to, like the one that has the largest probability, or do you have some more sophisticated sampling from the distribution?
It's a bit more sophisticated. We do top K sampling, so that means you take the 40 that are most likely. You renormalize the probabilities on those, and then you sample from that. That's a standard thing that people do and tends to be better. Yeah, and then you can choose the optimal temperature. We worked a bit to figure out like what the best temperature is for this kind of thing. Yeah.
Have you seen examples of error where it's purely algebraic error, for example? And if so, could you have augmented either mathematical or SymPy capabilities in the training so that it doesn't make symbolic or algebraic errors, for example?
Yeah, there are lots of questions. There are lots of mistakes like this. So for example, here, it's like a dancer spinning, the dancer spin 2250 degrees, and then which is 5 360 degrees and 150 degrees, and that's not correct. So, but you can see also the problem here is that it's not like all the calculations are just 2250 equals 360. Sometimes it just uses English to do the calculations. So it's not so easy to take this and kind of feed it into a calculator. You have to deal with the fact that it does things in using English and informal language. But yeah, there are lots of calculation mistakes. Yeah.
Any plan to try these on mathematical textbooks? To see like whether it perform better or not, and like the whole set of elementary school and middle school and university, and also maybe that can be used to evaluate different textbooks.
Yeah, I think that would be an interesting thing to do. Yeah.
So one would think that there are some basic skills that someone who knows math would have, like dividing fractions and multi-step logical reasoning. So how well does it can you quantify how well it does it do on those basic skills?
So the one thing we measured is basic arithmetic using this few shot prompt, and it does better than I can. So like it does, like this one is 8-digit addition. See, 8-digit or 9-digit addition, it does with over 80% accuracy without, it doesn't work it out. You just ask it this plus this, and it just gives the answer. So definitely better than I can do in my head. So it's pretty good at basic arithmetic, but it does still deteriorate. So it's not like it learned to do long addition and is now applying it to every addition problem or anything like that. It does it some other way.
Do you know what would happen if you ask, let's say for your 10 or 12-digit numbers where the actual accuracy is not great, whether if you ask it for A plus B plus C compared to A plus B plus C, just checking that addition is associative, would it know the answer to a question?
I haven't tried, but I'm sure it won't. Yeah. There's no way that will.
Let me ask you another question, like another sort of natural language thing. Let's say you give it a 20-digit number and say, what is this number in reverse?
Yes.
Is that an example of something that you could do?
Yeah, I think so. Yeah, these things are pretty good at doing stuff like that. Yeah. Also for words, you can ask them to reverse letters in words. And yeah. These things I think would be pretty, especially because it sees the numbers as the digits get tokenized. Every digit is a token. So actually reversing is like an almost trivial thing for it. Yeah.
Right. And maybe a final question along these lines. You give it a 20-digit number in base 10 and ask for it in base 2.
I haven't, yeah. My guess is that it will probably do like 20-digit. I can try, but I'd be surprised if it can do that for a 20-digit number with no chain of thought or anything, just prompting it and asking it to do that. Yeah, I'd be surprised for a 20-digit number if it could do that.
Yeah, obviously, all my questions are probing whether it has a representation of the number. And it.
I don't think it does. I would say this. I don't think it learned math like we learned math and is using this representation. It does it some other way, which I don't understand, but doesn't really generalize that well to things like this. Yeah.
Actually, sorry, maybe a final question just about arithmetic, because in Jared's talk, I think someone asked GPT-3 to add 2 9-digit numbers, and it was pretty good at doing it if you separated the 9 digits with commas. Is this sort of just for arithmetic? Is it better than other things just for arithmetic, or is it pretty much just as well?
This is the best model I think we have for basic arithmetic, as far as I know. Which is not so surprising because it has seen a lot more math than all the other models. Yeah.
Given that we sampled all the archive papers, could we feed the model our paper without the introduction and ask it to write it?
It does a decent job. Yeah, you can also like you can make an abstract. You can ask it to add citations where like you're not sure what the citation is. It's decent at these things. Yeah.
Answering questions, there is directly say with the alpha board prompt, which is a totally different way of getting the answers.
Yes.
How will you do compared to that?
For questions like this, like these ones? Like
We
these
have a
ones?
question to ask a question that you can ask both of them. How will you do?
Well, it really depends on the question. You know, if you're asking it to add up to large numbers, then it will do very poorly. But if you ask it like this complicated question that requires a step-by-step solution, then, and the numbers are typical, then it will probably do better. Depend, yeah, really depends. Or if you ask it to do an integral, it depends on how you ask. So if you prompt it with integrals, it does really well on doing symbolic integrals. Like it will do integration by parts, it will do a bunch of stuff, but it will often still make mistakes. Wolfram Alpha, you know, will just solve any integral with no mistakes typically. Yeah, it depends.
Let's say we are only interested in the final answer in these kind of questions. Does it perform better if we prompt it with the just final answer or if we prompt it with the solution?
Oh, way better when you prompt it with the chain of thought. Yes. Because otherwise you're asking it to almost guess. And in like one forward pass, just say what the answer is. With the chain of thought, you're actually, like in CS terms, you're letting it use a lot more computation to arrive at the answer, right? And like
Even though the training set is the same, so just the prompt and guess.
yes. Yeah. If you just ask it for the final answer, it will not do well at all.
Is there any way of incorporating the Wolfram Alpha method and this method in a hybrid manner so that it learns some sort of mathematical logic and does things more logically? Because this thing doesn't do anything logically, right?
Yeah, there's no hard logic in here. I think that's a very interesting open question of how to combine like systems that do hard logic with this kind of soft logic things. And there is a very nice paper on autoformalization that I think is a nice step in this direction. So what they do is they ask these models, that was for Codex from OpenAI, but it's a very similar idea. They ask the model to prove a theorem and it produces a proof using just informal English. And then they ask the model to translate that proof to formal language. They use Isabelle. So this is one of these formal theorem proving languages. So these models are actually pretty good at translating. And so they're able in some cases to take the informal proof and turn it into code that you can then feed into a formal theorem prover to verify your proof. So that's one way that maybe is a good way of bridging this gap between soft and hard logic is by asking models to translate their soft answers into code that you can then feed into Python or Isabelle or whatever it is. So that's, but it's still an open question. Like how to combine these systems is an open question, and we have just like some initial ideas, I would say, for how to do that.
So,
Thanks.
you, for example, is this a question that was in the data set?
No, I don't think this.
Because it says that the problem source was some high school physics.
It's a benchmark, yeah. It's just oh, sorry. The model just what the model did was just model answer. Everything else here we generated just saying where it came from.
Right, but if was this, so it came from somewhere.
Yeah, this benchmark called MMOU.
Yeah, and was that in the data that it trained on?
No, I don't think so. No.
Because otherwise it would have found exactly this question that we just.
Yes, we just spit out the answer. Yeah. Oops, sorry. So we tried to find questions, we tried to find answers in the data set. We didn't find this one. We found a couple of others, but we found very few. I mean, this question of like how much of this was memorized. I mean, I'm personally convinced that not much, because I made up questions and it could just answer them. So I kind of, and it was kind of at the same rough level as these kinds of questions. But I think to really test these, but I also learned that it's very, very difficult to go and try to find the question in the data set, because, you know, if one of the words was slightly different, these models would just, they don't care anymore about things like that. So really the way to test these things is to, well, one trick is to say, okay, we collected the data that was online up to this point in time. And now we're only going to test it on questions that came after. Now you're guaranteed that there was no, that's the only way I know to get around these things. Yeah.
Is it good if you add a bunch of extraneous information? Have you tried that? Like if you just dressed this problem up just in the middle with sentences that don't matter about the stone. Oh, the stone was this color and this guy drew it.
Like a story.
And you just, yeah, and it just sees, does that derail it or?
I haven't tried.
Hmm.
My guess is no. If you don't do too much of that, my guess is no, but but you know, you could, here's something that could like really trip it up is you say, please ignore the following question and answer the one that comes after. And then ask it two questions, whether or not it would actually ignore the first and answer. I'm kind of doubtful that it's because now you're pushing it out of its training distribution. It's probably hasn't seen like a lot of stuff like that. And it doesn't actually apply logic. You know, there's no mechanism in there by which it says like, okay, logically, I only need to answer this. And so from now on, I'm just going to, it's all soft attention masks. So I would say it's pretty easy to trip it up in ways like this if you want to.
It's kind of similar question, but just if you change slightly the wording, like if it's stone with rock, like would the solution be accepted the same with stone substituted to rock, or would it be like something very different, even if the result is the same? I will state what it is from irrelevant modification. Modification, not addition, even like just modifications.
So these things are stochastic in the sense that we're sampling with temperature. So it's a bit different every time anyway. But yeah, we tried taking questions and like changing the phrasing or changing the numbers. And well, you can see this is like accuracy versus the accuracy of the modified questions. It moves a bit, but there's no clear trend. It's not like it becomes better or worse. So it's fairly insensitive, I would say, in terms of performance. And with the detailed answer change, again, like every time we sample, we get something else. So
the logical steps could be even different.
It could be different.
But then
yeah.
But for the actual aspects, like the language aspects, presumably the pre-trained model that you used would already take care of that, right? Like rock and stone would probably have very similar embeddings and you wouldn't have to worry about that.
Yeah, I mean, that's the hope, but that's why it's a way to test whether the model is.
No, I'm not sure I mean, I think that would probably already be an aspect of whatever pre-trained model to use.
Maybe along these lines, what if you changed it to like just a nonsense word, like a zoitzol is thrown with blah blah and so on. Yeah. What happens then?
Yeah, like so I think the closest to that I've tried is to say something like, for the purpose of this question, foo means multiplication, and I'll write foo everywhere, and it doesn't do well on that. It doesn't, again, this is like where it needs to, it had, well, this is all speculative. I can just say it doesn't do well on that. Let's say it like that. Because again, it's a non-typical thing to do, and once you ask it something non-typical, it will just very quickly do much worse.
You have access to this in your laptop and you see.
Actually, guys, my question was a little bit was less interesting than what you're doing. I mean, it's really sort of probing whether the fact that it's doing well with stone and rock and something has something to do with the fact that stone and rock show up in physics problems, versus whether it really, yeah. Well, you know what I'm saying. So yes, it'll be interesting to see if it did as well with zoitzol as with stone or rock.
Sure. Yes. Yeah, I hard for me to predict if that would make a difference or not. Yeah.
What practical use do you see for these models in near future, or what kinds of models like this, like supersymmetric Lagrangian transformation, something like that?
Yeah. So I think. I mean, one obvious application is for math tutoring or science tutoring. This thing is not a good tutor like out of the box, but probably if we train it like on transcripts from some online, education website or something like that, it would probably become quite a bit better at dialogue and would maybe be able to interact with students. And the problem there is that for tutoring, the bar for accuracy is very high because, I'm very happy when it can do like 80% of math questions well, but that's not good enough when it talks to a student. So definitely there's definitely more to be done for that to be useful there. And the other thing is as a kind of research assistant. So this could be something that helps with symbolic calculations. It could be something that helps with writing papers. It could be I've tried it with brainstorming, like I asked it to like, I did this on some machine learning question, but I said like, okay, we're just like, here's an introduction and in this work, we are working on like the problem of getting language models to do blah, and we did this by, and then I just let it complete. And it spit out something that was like pretty sensible. Like we did this by collecting this kind of data from this website and train a model on. So it was pretty sensible and kind of fun to interact with. But I think probably near term is kind of turning it into some kind of research assistant. That's probably feasible because if you're a researcher, you're an expert. And so if the model spits out some nonsense, that's not too bad. You can recognize that it's wrong and just ignore it. So the bar is lower. Yeah. So these are two applications that make sense.
It's so exciting that we probably continue all day. We can do that informally, at least until we go to dinner, but then we can continue over dinner. This reminds me, if you're interested in joining us, please send me an email in the next 10 minutes or so, a quarter of an hour, and we'll meet at 6. And let's thank Guy again for a very